Hey everyone! So today, we are tackling one of the biggest challenges in system design. What do you do when your database gets just way too big for a single machine? We're going to go deep on a technique called partitioning, or as you've probably heard it called, sharding. Honestly, it's the key to handling absolutely massive datasets and getting to incredible scale. All right, so picture this. You've hit the wall. Your database server's CPU is just pegged at 100%. You're literally running out of disk space, and queries are getting slower and slower and slower. You've optimized everything you can think of, but the data just keeps pouring in, right? Think of a social media app. Every new user, every post, every single like just adds to this massive pile. This is that moment every engineer eventually faces. So, what's next? What's the logical step? And the answer is partitioning. So instead of trying to buy a bigger and bigger server, which we call scaling up, we're going to scale out. We take our giant database and we break it into smaller, more manageable, independent chunks. We call these partitions. And then we spread them across a whole bunch of different machines. What this means is each machine gets its own CPU, its own memory, its own disk, so a query that hits one partition doesn't slow down queries hitting another. The goal here is simple: massive, massive scalability. Okay. Here's the game plan for this explainer. We're going to start with the why. Why even bother with partitioning? Then we'll get into the two main strategies, range versus hash. After that, we dive into the really tricky parts, like how to handle secondary indexes, what to do when you need to rebalance data as your cluster grows, and finally, how your application actually finds the right piece of data in this whole distributed setup. So, let's kick it off. Section 1. Why do we do this? Well, the main reason, like we said, is to spread the load. By distributing all that data across many disks and spreading the query load across many processors, a 10-node cluster can, in theory, handle 10 times the workload of a single node. It's all about sharing the work. Now, this is a really important point, and it trips a lot of people up. Partitioning is not the same thing as replication. Partitioning splits the data up for scale, so you can handle more traffic. Replication copies the data for fault tolerance, so you don't lose anything if a server dies. In the real world, you absolutely do both, and this diagram shows it perfectly. See how each node can be a leader for some partitions, holding the main copy, and a follower for others, holding the backups? This combo gives you both scale and safety. Okay, moving on, we know we need to split the data, but how? How do we decide which records go into which partition? This really boils down to two fundamental approaches: partitioning by a range of keys, or partitioning by a hash of the key. First up, range partitioning. And you know what? The encyclopedia analogy on this slide is just perfect. If you want to look up Ottawa, you know exactly which volume to grab. Databases do the same thing. Partition 1 might hold all the keys from A through C, partition 2 gets D through F, and you get the idea. The huge, massive advantage here is that range queries are incredibly efficient. Need all the sensor readings from last Tuesday? Boom, they're all sitting right next to each other in one partition. Easy. But, and this is a big but, there is a serious downside: hotspots. Let's stick with that sensor example. If your key is the timestamp and you're constantly writing new data, where do all those writes go? To the partition for today, right? This means one partition's CPU and disk are just getting absolutely hammered with all the new write traffic, while all the other partitions for last week, last month are just sitting there, totally idle. You've paid for this big 10-node cluster, but you're only really using the power of one. This completely undermines our goal of spreading the load. So to solve that hotspot problem, we use hash partitioning. Here's the idea. You take your key and you run it through a good hash function, something like MD5. You can think of a hash function as just a deterministic scrambler. It takes any input and always spits out the same, totally random-looking number. Then you assign ranges of these hash values to your partitions. So as the slide shows, even keys that are super close together, like timestamps that are only a second apart, will have wildly different hashes. And that scatters them beautifully and evenly across all your partitions. And this brings us to the crucial trade-off. This is really the whole ballgame. With range partitioning, you get those awesome, efficient range scans, but you run the risk of creating hotspots. With hash partitioning, you get beautiful, even load distribution, but you totally lose the ability to do efficient range queries. If you want to find all the users created in March, well, now you have to go ask every single partition because their data is scattered everywhere. But even hashing isn't a perfect silver bullet. This brings us to a more advanced senior-level concept, the celebrity problem. Imagine a celebrity posts something and gets a million comments. Now, if you're partitioning by the post ID, even if you hash it, it's still just one hash value, right? All 1 million writes are trying to go to the exact same partition, and bam, you've got a massive hotspot. A common solution is to add a random number, or a salt, to the end of the key before you hash it. So instead of just hashing post ID 123, the application might hash post ID 1231, post ID 1232, and so on, maybe up to 100. This effectively splits the writes for that one hotkey across 100 different partitions, spreading the load out. Okay, so we've figured out how to partition our primary data, but what about just searching for things? You know, if your main key is a unique listing ID, how in the world do you find all the red cars for sale? This is the huge challenge of secondary indexes in a partitioned world. The first approach is what we call a local index. It's simple. Each partition is basically its own little self-contained database. It keeps an index of only the data it holds. This makes writes pretty fast, but like the diagram shows, to find all the red cars, you basically have to shout your query at every single partition and then stitch the results together yourself. This is known as scatter-gather, and it can be really slow and expensive because your query is only as fast as your slowest partition. Now, the alternative is a global index. Here, the index itself is also partitioned, but it's partitioned by the term you're searching for, like the color. So the index for colors A through R might be on partition 0 and S through Z on partition 1. This makes reads super fast. To find red cars, you know to go directly to partition 0. But the trade-off is that writes become way more complex. Adding one new red car might require what's called a distributed transaction, a coordinated write across multiple machines to update both the data partition and the index partition. And that's way harder to manage and can be a lot slower. All right, let's keep moving. So your system is growing, it's successful, and you need to add more servers to your cluster. This means you have to start moving data around. This process is called rebalancing, and trust me, doing it without causing total chaos is absolutely critical. So, how do we rebalance without all the drama? Well, a really common and clever strategy is to create way more partitions than you have nodes, right from the very beginning. So you might have, say, 1,000 partitions running on just 10 servers. Now, as this slide shows so well, when a new node joins the cluster, it doesn't cause some massive data reshuffle. It simply steals a few complete partitions from the existing nodes until the load is balanced again. This keeps data movement to a minimum and is way less disruptive. And here is another piece of hard-won wisdom from the trenches. Fully automated rebalancing can be super dangerous. Imagine one of your nodes is just temporarily overloaded and it's slow to respond. An automated system might see that, think it's dead, and immediately start a massive rebalancing operation to move all its data. It's kind of like seeing one person in a bucket brigade stumble and deciding the solution is to make everyone else pass buckets faster. All that does is put even more load on the network and the other nodes, and it can cause a cascading failure that takes down your whole system. A lot of times, it's much safer to have a system that suggests a rebalance, but requires a human to actually push the button. Okay, we've reached the final piece of our puzzle. We've partitioned our data, we've figured out how to rebalance it across our nodes. Now, when a client application wants to read or write a piece of data, how does it know which machine's IP address to connect to? Well, this slide lays out the three main patterns, and they each have their own trade-offs. First, you could connect to any random node, and if it doesn't have the data you want, it just forwards your request to the right one. That's simple, but it adds an extra network hop. Second, you could have a dedicated routing tier, basically a smart load balancer that knows where everything lives. That's a clean architecture, but it's one more thing you have to manage. Or third, the client application itself can be smart enough to know the partition map and connect directly. This is the most efficient, for sure, but it makes your application code a lot more complex. And that brings us to our final thought for today. Partitioning is an incredibly powerful tool for scaling, but as we've seen through all of this, it is not free. It solves the problem of data volume by distributing the data, but in exchange, it distributes complexity across your entire system. You're constantly making these trade-offs. Do I want range scans or even load? Do I want fast reads or simple writes? So the final question to leave you with is, when you're designing your own system, which of these trade-offs is the most critical one for you to get right?